Hello again, this is Professor Roman. We continue the lecture series, Transition to Advanced Mathematics. We have completed our look at proof techniques. I hope it is something you will continue to practice, however. I would suggest reviewing the material on proof techniques, trying to prove some of the theorems that are listed there without looking at the proof in the book. Just remember, practice, practice, practice. That's the only way to get this down. Now we're going to talk about sets and multisets. Sets do not allow for duplicate elements. An element, that is to say a set, either belongs to a given set or it does not. And that's the end. So if you see something written like this in set braces 2, 2, 3, I suppose you would say to yourself, well, there's a little mistake here because 2 is either an element of this set or it's not, and so it is that this is really the set containing 2, 3, where the author made a little mistake. Well, sometimes it's quite useful to be able to include duplicate elements in a set. As a simple example, this equation, we'd like to be able to say it has, since it has degree 3, that it has 3 roots, or 3 solutions. So we want to say that the solution set of this equation is 2, 2, 3. Where the solution 2 really does appear twice, and we refer to it as a double root of the polynomial on the left here. So there's something inconsistent about calling this a solution set when it isn't really a set if 2 appears twice. So to deal with this situation and other situations throughout mathematics, in fact, there is a concept called multiset. Multisets don't receive anywhere near the attention that they deserve, and I don't know why. It's not a very complicated idea, and it's a very useful idea. But for some reason, it just doesn't receive enough attention. And in fact, this idea, it seems, was first used as early as 1150 by an Indian mathematician whose name I wouldn't even begin to try to pronounce. The idea behind the notion of a multiset, and this isn't the formal definition, but just the idea, is the following. A multiset M is a collection in which a single element may be repeated more than once. The number of times that an element is repeated is called the multiplicity of the element. A multiset in which at least one element has multiplicity greater than 1, and therefore it's not a set, is called a proper multiset. Sets are multisets in which every element has multiplicity 1. Unfortunately, there's no standard notation to represent multisets. So you will often see something written like this. And now, contrary to what I said at first, you would have to decide, was this a mistake or is this intended to be a multiset? And it's probably the latter. I've never met a mathematician who would make this mistake and write this instead of the set 2, 3. That's just, it's just not going to happen. So if you see this, you should probably think this is a multiset. A better notation would be double braces, and then there'd be no ambiguity. But again, this is not standard notation, but I'm going to use it because it'll help clarify. Now, what about a formal definition of multiset? Well, everything in mathematics that's not a proper class is a set. And so multisets are sets. The question is, what sets? So here is the formal definition. Let S be a set, then a multiset M is a set of ordered pairs, and these ordered pairs, the first coordinate, little s, belongs to the set, capital S, and the second coordinate, M of S, is a positive integer. And M of S is called the multiplicity of the element S. And so intuitively that represents the number of times that little s appears in the multiset. The subset of capital S that consists of the first coordinates, we're not saying here that every little s and big S has to appear in an ordered pair. All we're saying is the converse. The first coordinates of every ordered pair belong to the set capital S. If we collect the first coordinates together, we will get a set. It'll be a subset of capital S, and that is referred to as the underlying set for the multiset. So another way to say it is take the multiset, write it informally like this, and toss out all the duplicates. And what's left will be a set. It'll be the underlying set for the multiset. So the underlying set here is just the set 2, 3. Here's another example of a multiset. Informally, we could write it this way. And that's how we generally will do. Formally, the number 1 appears once, the number 2 appears once, the number 3 appears 3 times, multiplicity 3, 4 has multiplicity 2, 5 has multiplicity 1. The underlying set then is what you would get by casting out duplicates, and it would be 1, 2, 3, 4, 5. Two multisets are equal if they have the same underlying set, and if each element in the underlying set has the same multiplicity in each multiset. So for example, if you look at these two multisets, and I've already violated my own rule, so I better fix that and put double braces. This multiset and this multiset do have the same underlying set, 2, 3, but 2 has different multiplicities, and so these are not the same multiset. And I guess that's pretty obvious. Okay? So again, the idea is very simple. A multiset is a set with the exception of the fact that elements can appear more than once. And each element has a multiplicity that tells you how many times it appears. Throughout mathematics, you're going to encounter special collections or families of sets. The power set, for example, is one such. It's a collection of subsets of the parent set, of all subsets, in fact. A set of sets is just what it sounds like. It's a set whose elements are sets. Okay? Now, we already know that everything in mathematics is a set or a proper class, but proper classes are not allowed to be elements of anything. And so all non-empty sets are sets of sets. Any non-empty set has elements. Those elements are sets because they can't be proper classes. And so all non-empty sets are sets of sets. So that's nothing new. So the term set of sets tends to be used mainly for emphasis. Let me explain. This set, containing the numbers 1 through 4, remember that these numbers are sets. Remember, 1 is the set containing the empty set, and so on. This is a set of sets, as everything is, but nobody would refer to it that way. You would refer to this, obviously, as a set of natural numbers. But this would be referred to as a set of sets, or even a set of sets of natural numbers. Okay? So don't panic by this repetition, set of sets. It's not that big a deal. Okay? Now, speaking precisely, a family of sets that allows duplicates, so I can't call it a set of sets. What do I call it? A multiset of sets. Here's an example. I did use the multiset notation. The set containing 1 is repeated twice, has multiplicity 2. The set containing 1, 2 appears once. The set containing 1, 2, 3 has multiplicity 3. So in formal notation, it would look like this. Set notation, ordered pair, set containing 1 appears twice, or with multiplicity 2. Set containing 1, 2 has multiplicity 1. Set containing 1, 2, 3 has multiplicity 3. For example, the power set of a set is a set of sets, a set of subsets of some parent set. Oh, S. But the roots of a polynomial will often be a multiset of real numbers, complex numbers, whatever, because there may be duplicate roots, double roots, triple roots, whatever. Well, this is, after you've read this a few times, after you've given it some thought, it should be fairly comfortable to you. But there's a bit of bad news. Unfortunately, the very common expression family of sets or collection of sets are used in two different ways by mathematicians. Some use the phrases to mean set of sets, so no duplicates allowed. Families or collections don't have duplicates. Others allow duplicates, and therefore families of sets, collections of sets, mean multisets of sets. So when you are reading another source and you come across the term family of sets or collection of sets, you don't know which the author is, which meaning the author has adopted until you search for the meaning. So you have to look in the index of the book, or hopefully you can figure it out. Sometimes it's not easy. The best way to avoid any confusion would be for you to write, let F be a family of sets with no duplicate members. Then it's clear you're talking about a set of sets. Or you can simply use the phrase set of sets. or let F be a family of sets in which duplicate members are allowed. That's clear, but you could also say multiset of sets. So that's the situation. The terminology, unfortunately, is not consistent. It's surprising how often that happens in mathematics. Definitions are supposed to be sacrosanct. They're supposed to be written carefully. They're supposed to be consistent throughout mathematics because they are one of our fundamental concepts. But unfortunately, that does not always happen. Terms, an author will decide to use a term in a certain way, and another author will decide to use a term in a different way. And it's just something we have to live with. But it can be rather confusing at times. Let's talk about indexed families. So when I use the word family, I may mean set or I may mean multiset. It depends on the context. And I'll try to make it clear. Indexing is a very useful tool for uniquely identifying objects, in particular elements of a set. For example, students at a university are indexed by their student IDs. Vehicles are indexed by their VIN numbers. Even buildings are indexed by their addresses. It's a way to identify objects. And so it is within mathematics. Both sets and multisets can be indexed. So we have the term indexed set and indexed multiset. But unfortunately, the more common terms for these objects are indexed family or indexed collection. And so here again, we need to check to see if duplicates are allowed or not. Maybe somebody should invent the terms family and multifamily and collection and multi-collection. And the problem with doing that now is that it wouldn't take throughout the mathematical community, so it would still, the terms family and collection would still remain ambiguous. So we just have to live with it. The informal definition of an indexed family, and by family I mean either set or multiset, is that every occurrence of every element in the family gets a distinct index. Not just every element, but every occurrence of every element. Now that applies to the multiset case. In the set case, every element has occurrence. One only occurs once. The index, the collection of indices that index the elements of the family, I'll generally use the letter I for that, is called the index set for the family. So for example, you'll often see a set or multiset written using a notation like this or like this. And you can see the indices 1, 2, 3 in both cases. So the index set is I3, 1, 2, 3. So again, I want to emphasize, for a multiset, every occurrence of an element gets a different index. The formal way to describe indexing is with a function. So here's the formal definition. An indexing of a family F, again set or multiset, is a function from a non-empty set I, known as the index set, to the family F. the function is called an indexing function. And if little I belongs to the index set, then f of little I is the element of f that is indexed by, or that has index I. And when a family has been indexed by some indexing function, we call it an indexed family. A family can be indexed by different index sets. Indexing is not a unique process. There are generally many ways to index a set. Here's a picture, might help keep this in your mind, of an indexing function for this set, ABC, and this multiset, and I did it again. Sorry about that. For this multiset. So F maps 1 to A, 2 to B, 3 to C. Could have done it differently. Could have mapped 1 to B and 2 to C and 3 to A. It's a different indexing function. And it is, in a sense, a different indexed set. The underlying set is the same, but the indexing is different. And here's a way to index a multiset. So notice that B has multiplicity 2, but it gets 2 different indices. So these are treated as different. One way to think of it that might help, I suppose, is imagine the elements of every multiset are colored with different colors. And so these two B's are colored differently. To help identify them as being 2 different occurrences of B. And so different colors should get different indices. In common practice, we seldom use an indexing function explicitly. But sometimes it may be necessary for clarity, but usually not. Usually we write an indexed function, an indexed family as something like this. F equals the set containing A sub I, where I ranges over capital I, which is the indexing set. For a finite family, we generally write this. You're probably used to seeing this kind of thing. It's worth emphasizing that any set can be an indexing set, but usually we pick, for finite families anyway, we pick natural numbers. And usually the indexing will start with either 0 or 1. But you could index using rational numbers that start at 17 if you wanted to for some reason, or negative 24. Doesn't matter if you have a reason for doing so. It's possible that if you were indexing a set and you knew that in a minute you were going to add another element to the set, you might want to start the indexing at 2 so that your new element could have an index of 1. Anything is possible. So that's the story on indexing a set. And it's extremely common because it's the easiest way to identify the elements of a set. Okay, let's now talk about set operations, many of which you may very well be familiar with. Union, intersection, relative complement, symmetric difference. We have actually used some of these operations earlier in the book, but this is the right time to gather them all together in one place. First, I repeated the definition of subset just for reference. A set A is a subset of a set B, denoted this way if every element of A is also an element of B. or in symbols, x in A implies x in B. And a subset A of a set B is called a proper subset of B, denoted this way, if it's a subset but it's not equal to B. And I should also mention, which I think I did before, that there is a little inconsistency in notation as well. There are mathematicians who use this symbol that we're using for proper subset for any subset, and then they have to use a different symbol for proper subset. So here are the definitions. Let A and B be sets. Figure 5.1 here shows what are called the Venn diagrams for the various set operations that are defined below. And the result of each operation is shaded in dark shade. So the union of the sets A and B is by definition the set of all elements, or the set of all sets, that lie in either A or B. So formally it would look like this. The set of all sets X such that X is in A or X is in B. And that's the shaded region here. The intersection of A and B is the set of all sets that lie in both A and B. So the change from here to here is change the disjunction to conjunction. It could also be written this way: the set of all X in A such that X is in B as well. And so that's this shaded portion here. The set difference A minus B is, and this is not the usual negative sign or minus sign that's used for numbers. Some authors I've noticed do use an ordinary minus sign. I don't like that, but that's just personal taste. But for this course, do not use this symbol. Use the slant. This is the set of all elements of A that do not belong to B. So set of all X, sets X such that X is in A and X is not in B could also be written this way. And this is the relative complement, the set difference A of A minus B. Okay. The set difference is also called the relative complement of B in A. So be careful here. It's not the relative complement of A in B, it's the relative complement of B in A. Complement means not, basically, everything else but. So this is everything in A but except for the things that are in B. The relative complement of B in A. And it's not good enough to say relative complement of B and stop. You have to say what it's a relative complement in. A special case of the relative complement occurs if there's a universal set, and then the relative complement of A becomes the complement of A. The relative complement of A in the universe becomes simply the complement of A. So here's the picture. I have a universe now, and here is A. The relative complement of A in U minus A, you could leave it written that way, that's perfectly fine. but it is also referred to as the complement of A, and it's this outside region. Now, this is a little bit dangerous. One often hears people say, take the complement of the set A, and unless it's obvious, your response to that should be the complement in what? What's the universe? Because you change the universe, you're going to change the complement. So the notion of complement by itself depends on a universe, which must be clearly specified. Also, the notation is somewhat lacking because there's no indication in the notation A superscript C of what the universe is. If you write U minus A, everything is there, both the universe and the set you're complementing. So in many ways, this is better notation and better terminology, the relative complement of A and U. The symmetric difference of A and B is the set of all elements in the union that do not lie in the intersection. So the simplest way to get a hold of that is with a picture. Everything that's either in A or B, but not in both. That's called the symmetric difference. You can see where the term symmetric comes from. It looks rather symmetric, the shaded portion. A common notation for symmetric difference is delta, capital delta, or a triangle. So the symmetric difference can be written in several different ways. Here is the sort of the direct translation to symbols. X is in the union, but X is not in the intersection. Set of all X in A union B such that X is not in A intersect B. Here's another way to write it. It's the set difference, A union B minus, take away A intersect B. But it's also equal to A minus B, which would be this half, the shaded portion, union B minus A, which is the other shaded portion. So there's various ways to write the symmetric difference. Unions and intersections extend rather easily to families of sets. Here is an indexed family of sets. Okay. Again, this could be a set of sets or a multiset of sets. The union of the family is the set of all elements that lie in at least one member of the family. I think I'll add here, or I say family just to be consistent, set or multiset. So the union of the family is the set of all elements that lie in at least one member of the family. And there are several notations for that, and you should become comfortable with all of these notations because they appear quite frequently. The simplest, and in many ways the best, is the one you see the least often, big U for union, family F. You're more likely to see something like this, the union of the A sub i's, as I ranges over the index set I. This is awkward notation if you're going to put it inline text. So this is another common notation, the union of the set of all A sub I such that little I is in big I. And this is in fact the definition, the set of all sets X such that there exists an index little I and big I such that X is in A sub little I. So I would urge you to look over this until it all seems quite clear to you and you can write it down yourself without looking at this. Intersection of the family F is the set of all sets that lie in every member of the family. And so the notation's very similar. Intersection F, intersection A sub I ranges over the index set. This notation looks just like that, with the union replaced by intersection. Definition. When the family F is a finite family, it's quite common to write union I goes from 1 to n. Now the index set now are the natural numbers from 1 to n. So we write I goes from 1 to n of A sub I, and the same for the intersection. Or written out more explicitly this way. Which of these is more useful? They're equally useful, just depends on the circumstances. Properties of set operations. Here we have 7 properties, but not to panic because several of them are the same or analogous to properties of ordinary arithmetic of real numbers. But let's look at them. Properties of the empty set. It should be pretty obvious that when you take a set A union the empty set, you just get A. This adds no elements to the union. A intersect the empty set is going to be the empty set. Idempotent properties, A union A is A intersect A is A. These don't have corresponding properties for the real numbers in arithmetic. But these 3 do. Commutative laws, A union B is the same as B union A, same for intersection. Associative laws, distributive laws. I'll let you study those. They have analogs in arithmetic. Properties of the complement. We have a universe U. The complement of the empty set is the entire universe. The complement of the universe is the empty set. Take the union of A and its complement, you get the universe. You take the intersection of A and its complement, you get the empty set. Complement is an involution. Do it twice, get back to where you started. This is the most interesting in a way, and it is De Morgan's laws. Again, we had the version for propositional logic. Now we have a version of De Morgan's laws for set operations. The complement of the union is the intersection of the complements. Complement of the intersection is the union of the complements. It's very similar to the version we had for logic. Instead of swapping disjunction and conjunction, you swap union and intersection. And complement plays the role of negation. To prove all these is pretty much a matter of just applying the definition of equality of sets. 2 sets are equal if they have the same elements, or to use the subset property. So 2 sets are equal if and only if each is a subset of the other. Okay, so also the subset property, you might say. So S equals T if and only if S is contained in T and T is contained in S. Okay. So just to illustrate, to prove a commutative law, X is in A union B if and only if X is in A and, or X is in B if and only if X is in B or X is in A if and only if X is in B union A. Okay. So it's the commutativity of disjunction that translates in the commutativity of union. So I've left the proofs of the rest of these for you. It's good practice. Do it once, you'll never have to do it again. We've seen the use of Venn diagrams in an earlier figure to describe the union, intersection, set difference, and symmetric difference. But Venn diagrams involving two sets are fairly limited, not terribly much use beyond what we did use them for. Venn diagrams really come into their own when you have three sets. And just to illustrate, we can use a Venn diagram to demonstrate the distributive law. So here's the picture. We have three sets. They must be drawn this way so that there's all possible overlaps. So region 4 here is the 4 and 7 are the overlaps for A and B. 7 and 6 are the overlaps for A and C. 7 contains the elements in common to all three. In other words, the intersection of all three. Okay. 7 and 5 contain the overlaps between B and C, or the intersection. Now, the left side here consists of all the elements of A that are also in, that's what the intersection means, also in B union C. Okay. So where are those elements? Which regions? They have to be in A, but then they also have to be in either B or C. Okay. So those regions are 4, 6, and 7. Those are all in A, but each of those regions belongs either to B or C. 7 is the only one that belongs to both B and C. So that's the shaded portion here. Now we look at the right side of the distributive law. A intersect B union A intersect C. A intersect B is this wedge here containing 4 and 7. A intersect C is the wedge here, 6 and 7. We take the union of 4, 7 and 6, 7. It's 4, 6, and 7. Same shaded area. So both sides of the distributive law define the dark shaded area here. Now, I should emphasize that this is not a formal proof. So this should be used as a guide. If you are given an equation involving sets, and you are asked, is this equation true or false? You could attempt to just prove it using the formal techniques of elements and subsets and so on. Or if you've got the time and you would like to decide whether to try to prove it's true or prove it's false, you can draw a Venn diagram. And if the equations are really complicated, even the Venn diagram may be difficult to figure out. But if it's not too bad, you will get insight from the Venn diagram. But it's just insight. It's not a formal proof. Let's talk about the empty family of sets. So the empty family has nothing in it, no elements. It might seem rather boring at first, and in many ways it is. In fact, in many ways it can be a nuisance, because one has to say, oh, well, this is true except for the empty family, and that sort of thing. But even though the empty family is devoid of content, it's actually somewhat interesting. Here's an example. Let me ask you a question. What do you think the union and intersection of the empty family should be? Okay. When I ask students in my classes that question, many students, not all, but many, most students won't answer at all. It seems to be typical, but those who do offer an answer, many of them will say that the union of the empty family is everything. Union, when you take a union, you're throwing stuff into a big pot, so it should get big, bigger than the individual pieces. So there's a tendency to say that the union of the empty family is the entire universe, whatever that is, and the intersection of the empty family is the empty set. So I'd like you to pause the video and think about that. Does that make sense to you? If it does, why does it make sense? How would you prove it? If it doesn't make sense to you, what does make sense? What do you think the union and intersection of the empty family should be? And try to prove that. So then let's resume. To validate our guesses, we need to construct a proof, a logical argument. So, according to the axiom of union, or just the definition of union, if you want, X is in the union of the empty family if and only if there exists a set A in the family for which X belongs to A. Well, that's enough to tell you what's going on. What about this? There exists an A in the empty family such that X is in A. False. There are no A. There are no elements A in the empty family. Empty family has nothing, no elements. So this is false. When you have a biconditional and you wish it to be true, both sides have to have the same truth value. Since this is false, this has to be false. This is false. The only way that's possible is if the union of the empty family is empty. Okay. So the union of the empty family is the empty set, not the whole universe. As to the intersection, we have this biconditional. Now let's look at this statement there, that for all A in the empty family, X is in A. This is true. It's true vacuously. For all A in the empty family, X is in A. Well, there are no A in the empty family. Okay, so this is true. Again, if the biconditional is to be true, then both sides have to have the same truth value, which means this has to be true. X in the intersection of the empty family. This really says for all sets X, X in the empty intersection of the family, if and only if this happens. I should have probably said that for the union too. So this then is true for all sets X, which means that the intersection of the empty family is the universe, which for us here, since it's unspecified, is the class of all sets, the proper class, in fact, of all sets. If there were a universe U, then this intersection would be the universe U. But since I haven't specified one, our assumption then is that it's all sets. So those students who felt, and quite reasonably or intuitively, that the unity of the empty family is everything and the intersection is nothing, got it backwards. Another example where intuition can fail. This is a really good example. Your intuition may have failed, but when you look at the definitions and you construct a logical, sound argument, a valid argument, you see the correct facts.